Niagara Falls. Majestic beauty. Natural wonder. And the symbol of electric power. It was here that the industry matured and that the modern electric system was established. This triumph, seen by many as the greatest engineering achievement of all time, is the story of this video. This story unfolds across the National Grid service territory. It was the people and the predecessor companies of National Grid who were the primary architects of this remarkable feat. We will cover events that occurred in the United Kingdom, New England, and in upstate New York. First, let's head to Great Barrington, Massachusetts to begin our story. Oblivious to the din inside the cavernous rubberware factory, nestled at the crook of the iced-over Housatonic River in Great Barrington, William Stanley surveys his laboratory. His steam boiler snorts impatiently. The temperamental Westinghouse steam engine finally hums comfortably. All is ready. It is time. Stanley knifes the switch. Alternating current surges through conductors that thread out of the building, past the barn where the town undertaker stables his horses, and into the village. The conductors are strung on the large elm trees that line the street. Along the way, his great achievement, his transformers, do their magic. The transformers step up the voltage for efficient delivery, and then step down the voltage to bring light to Great Barrington's Main Street. The transformers work to perfection. They are the heart of the system. As the 150 candle power incandescent lights snap to brightness, in the clothing store, the pharmacy, and in the doctor's office, the citizens of Great Barrington marvel. A new era begins.
I'm standing at the William Stanley Overlook in Great Barrington, Massachusetts. The rubber factory that Stanley used as his laboratory was located just across the Housatonic River. If you look closely, you can still see the foundation buried in a grove of trees. The time was March of 1886. Stanley's achievement was significant in a number of ways. It was America's first alternating current system. It demonstrated for the first time anywhere the use of his perfected transformers. And it was the first skirmish in the controversy that would be called the War of the Currents. To put the story in perspective, we need to look at the events and the people that brought us to this historic achievement.
In 1878, Charles Brush would patent the first successful arc lamp in the United States. The Brush system quickly showed its superiority to existing gas, oil, and candle systems, and electric lighting was on its way. The development of searchlights and fantastic lighting displays in theaters and World's Fairs stunned the public in the last decades of the 1800s. Electricity in Syracuse made its debut from the rooftop of an opera house in 1878. The banks and the bridges of the Erie Canal were jammed with people marveling at the spectacle of the arc light. 1 year later, in 1879, Thomas Edison finalized development of the incandescent lamp. Edison's lamp operated differently than the arc lamp. Instead of using an arc, the incandescent lamp used electric current to heat a filament until it glowed. The advantages of Edison's electric lamp over his major competition, gas lighting, were many. Less risk of fire, no danger of explosion, no flickering, no consumption of air, ease of control, a variety of colors, and immunity to wind or rain. Edison was careful to be sure his system was no more expensive than gas lighting competition. In 1882, Edison opened the first central electric station for supplying incandescent lamps on Pearl Street in Manhattan. Edison's system was successful, but its shortcomings soon became apparent. Most significant was its reliance on direct current, or DC. Because DC voltage cannot be easily changed, generation, distribution, and utilization had to operate at the same low voltage. This meant losses and voltage drops were quite high, limiting the distance that DC could be distributed to about a mile. Even with these limitations, Edison's system quickly became established in most major communities. It was superior to the gas lights, kerosene lamps, and candle lighting that it replaced. Lighting in general became a source of civic pride and changed the way people interacted with the night and their cities. Under a shimmering light, the ordinary seemed to acquire greater uniqueness and value. It minimized unattractive areas and idealized others. These changes soon became commonplace as electricity was integrated into the way people lived. And Great Barrington was no different. In 1886, an Edison DC system was installed at the Searles Castle. This was just 4 years after the Pearl Street station was established, and only 10 days before Stanley's experiment. The world was changing because of electricity, and all that was to be determined was the best way to make this happen on a broad scale.
It is ironic that one of Edison's direct current systems was active here in Great Barrington at the same time that Stanley was busy proving the viability of alternating current. Mary Hopkins, the widow of railroad tycoon Mark Hopkins, had architects McKim, Mead, and White wire her Main Street estate here at what is now known as Searles Castle for direct current. Just 10 days prior to Stanley's success with alternating current, her estate was lit with direct current. A few nearby dwellings were also connected to the system. All this took place at the opposite end of Main Street from Stanley's alternating current system. The noise from the engine powering the direct current generator in the basement was so loud that a remote plant had to be hastily constructed. Noise was not the only problem, and we will show you what happened when the two systems met in the heart of Great Barrington. But to understand this in greater detail, we will first take a brief detour into the technical story that is intertwined with this historical account.
As the world became fascinated by light in particular, and electricity in general, there was a parallel and connected story evolving in the scientific world. Let's begin this technical story with the basics. Let's look inside this flashlight to see how it works. As you can see, once the switch completes the circuit in the flashlight, the current begins to flow in one direction. This is DC, direct current. The current goes from the battery, which is the power source, through the load, the lamp, and returns to the power source. Early DC systems operated like this flashlight, with a DC generator as the source and lighting as the load. This was Edison's model. The story might have ended there, if not for the development of alternating current, AC. In the 1830s, Michael Faraday noticed that the motion of a magnet would produce a current in a wire. His discovery further linked magnetism and electricity, and paved the way for the development of AC. In addition to studying DC, scientists began looking more closely at the current that was produced by the motion of a magnet. They found that the changing polarity of the magnet caused electrical current to move back and forth in a conductor. This current was different from the DC that they had been used to studying. It vibrated or alternated back and forth. Faraday later developed his ideas into what came to be known as Faraday's law. A changing magnetic field induces an electromotive force in a nearby circuit, and this force causes a current to flow in that circuit. Faraday's discovery was developed into an alternating current generator in 1832 by Hippolyte Pixii. The alternating current is induced in the winding. This current alternates back and forth with the polarity of the magnet. The generator is not creating energy in this process. It is taking mechanical energy, the motion of the magnet, and transforming it into a different kind of energy, electrical energy. The induction principle works both ways. Just as a changing magnetic field induces a changing current induces a changing magnetic field, and this gives us the transformer. The rotating magnet in the generator creates an alternating current which, when applied to one winding, sets up an alternating magnetic field in the core of the transformer. An alternating magnetic field in the core induces an alternating current in the other winding. Transformers operate almost magically, as there is no electrical connection. The alternating current is induced from one circuit to the other through magnetism. Notice, on this transformer, that the number of turns in the winding on the right is different from the number of turns in the winding on the left. Changing the number of turns in the winding reconfigures the power by changing the two components of power, the current and the voltage. There are a number of things to point out about this animation. First, this transformer is stepping up the voltage as the number of turns in the winding on the right is greater than the number of turns in the winding on the left. The increased voltage will make the power travel over longer distances more easily. Second, the meters on either side are measuring current. You can see that they no longer indicate the same magnitude, as the current has been changed by the number of turns. Third, this transformer would likely be outside a generating station. The magnet is the generator, and the voltage is being stepped up for transmission. The transformer at a substation would look like this. This transformer is stepping down the voltage, which increases the current. You can see how the number of turns in the windings on either side is reversed from the last animation. We now have a way, with no moving parts, of stepping up the voltage and stepping down the current, and vice versa. Let's see how the magic of transformers and the flexibility of AC make our modern-day electric system possible. First, the generator, using a magnet, transforms mechanical energy into electrical energy. The energy is captured in a circuit, with the current alternating. Transformers reconfigure, in this case step up, the voltage for transmission. Electrical energy travels more efficiently at high voltage and low current levels. The transmission circuits interface with other transformers and substations, where the voltage is stepped down and the current is stepped up for use in distribution. Finally, transformers again step the voltage levels down from primary to secondary distribution levels for safer use in homes and businesses. Each time the voltage is stepped down, the current increases, but power always remains the same, except for losses in the system. Despite the proliferation of alternating current systems and their widespread use today, many still believe that the direct current model is the way that electricity works. In fact, AC works quite differently. The use of transformers gives AC tremendous flexibility, both in lighting applications and for motors. We have come to the end of our technical detour. Now let's go back to Great Barrington to continue the historical story.
So it was here in Great Barrington that Faraday's incredible discovery came to fruition, and William Stanley, working for George Westinghouse, was responsible. Stanley used a German-built generator driven by a Westinghouse steam engine to generate the power. He strung 4,000 feet of insulated wire on elm trees to deliver the power. But it was his handmade transformers, located in the basements of the buildings on Main Street, that were the genius and the heart of the system. Stanley's transformers demonstrated the viability and the versatility of alternating current, and its magic too. Transformers reconfigure and transfer power between circuits, using no electrical connection between them. They do their magic through the magnetic fields that couple the coils. The transformers were so efficient that there was very little drop in the voltage level needed to run the 150 candle power incandescent lamps. Westinghouse came quickly to Great Barrington to see the system in operation. Later that year, he would install the first commercial alternating current system in Buffalo, New York, 4 years after Thomas Edison had established his Pearl Street station in New York City. And the race between AC and DC was on.
The race was indeed on, and the stakes grew enormously when it was decided to harness the power of the Great Cataract at Niagara. Edison was among the first consulted by the newly formed Cataract Construction Company, whose mission was to transform the power of the mighty Niagara River into energy. A telegram was sent to Edison in France. Has power transmission reached such development that, in your judgment, seem practicable? His reply: no difficulty transferring unlimited power. Will assist. Sailing today. Edison lost no time developing his plan for a massive DC system at Niagara Falls. In November of 1889, he submitted his plan. His plan was costly, however, partly due to the price of copper. A French syndicate had taken control of the world's copper supply. An international commission was established by the Cataract Construction Company to resolve the matter. Edison interests were now desperate and knew that in order to win the war, they would have to exploit the hazards of alternating current systems. Edison Associates began electrocuting animals as big as elephants in town squares to demonstrate the dangers of AC. At the same time, New York State was searching for a more humane method to execute felons. Ever the opportunist, Edison and his associates convinced New York to use alternating current. In 1890, a convicted murderer from Buffalo was the first person to be executed in the electric chair. While the debate between AC and DC was raging at national and international levels, local communities, like Great Barrington, were seeing firsthand the advantages and disadvantages of the two systems for lighting. The growing realization that electricity had enormous potential for power applications, in addition to lighting, became a critical factor in making the final decision. And AC was also showing its superiority for lighting in communities like Great Barrington.
Our story comes together here on busy Main Street in Great Barrington. It was here that direct current from Searles Castle and alternating current from Stanley's system met. This building behind me, the Miller Hotel, was wired for both, making Great Barrington the first community to witness AC and DC systems in simultaneous operation. Stanley's system quickly showed the superiority and easily added more customers. The DC system's short range sat in stark contrast to the AC design and could not compete. 2 years later, in 1888, Nikola Tesla's AC motor received its first patents, marking yet another milestone in the story and raising the stakes even higher. Large-scale commercial systems were now ready to be developed.
The story unfolds like a great screenplay. A revolutionary theory developed by an unknown scientist. Great risk balanced by the potential of great reward. A backdrop of stunning natural beauty. And a dramatic moment when all the threads of the story are joined in a single hand. Nikola Tesla was the uncommon genius in the story. Tesla was born of Serbian parents in Croatia at the stroke of midnight during an electrical storm in July of 1856, and his life got more dramatic from there. As a young engineering student, Tesla saw that direct current was limited and that alternating current was superior in many ways. By the early 1890s, he had proven this to be true. His AC system was durable, powerful, and incredibly manageable, despite the tricky interplay of voltage, current, and magnetic field. His system used two separate alternating currents, both of the same frequency, but whose peaks and valleys were separated by a fixed time interval. This polyphase system was ideal for motors, capturing the power of electromagnetic fields to efficiently spin motors. By connecting each phase to a separate set of coils inside a motor, the resultant magnetic field would rotate around the bore of the motor, and the motor's rotor would follow the rotating magnetic field. It is testimony to Tesla's genius to have successfully choreographed this achievement at this time in history. Once George Westinghouse saw that Tesla's motors proved to run as well in reality as they did in his three-dimensional imagination, Westinghouse too became an advocate of AC, and soon the stewards of the Niagara Project were convinced as well. The war of the currents had a victor, alternating current, as championed by Tesla and Westinghouse. Led by Edward Dean Adams, the project forged ahead. In November of 1896, in a dramatic moment for the industry, the power from the Adams station was sent to Buffalo, over 20 miles away. This event proved the viability of bulk transmission of AC once and for all. By 1906, the transmission lines from Niagara had reached Syracuse, and shortly thereafter, New York City, and the world was forever changed. Electrical power could now be used for large-scale industrial application. When the Adams station went online, it was a pioneer and a wonder of the world. Today, Practically all of the electrical power in the world is produced and transmitted as polyphase alternating current, using Stanley's transformers, Tesla's genius, and the enterprising spirit of the human condition. Electricity is now the essential enabler of modern life. The electrification of the world is indeed the single greatest human achievement of all time, and much of this happened in the service territory of National Grid. From the work of Faraday in the UK, to William Stanley's work at Great Barrington, to the historic achievements at Niagara Falls, the people and predecessor companies of National Grid contributed to the development of electricity like no other. It is our hope that this video tells this story in a way that shows how inventive genius, courage, and tenacity come together to shed light on the enduring mystery that is electricity.